All right, so I also wanted to give you guys a demonstration of how PSI BLAST actually works, how we run the searches, and how we interpret the output. And so to start with, I went to the NCBI database and I looked up the protein sequence for the human version of hemoglobin beta. And so I'm going to first run a BLAST search, and this is going to be a little bit cooking show style because I've already run these searches and I'll be pulling up different tabs as I go so we don't have to wait for them to run. But here is my GenBank accession number. And so I can simply copy and paste that into the search box of my NCBI BLAST P window. And then, of course, I can scroll down. I'm doing a protein blast, click the magical blast button, and then the results will run. And so here are the results that I got previously from running that search. And so you'll notice that if I look at the graphic summary, which is where I always like to start with a blast, you can see that we have hits that are highly, highly similar to the original human hemoglobin beta protein. And we have hits that extend all the way across our query sequence for the most part. A few may be missing some ends of sequences, but we can see immediately that we're finding highly similar sequences. And if I go and look at my descriptions tab, these percent identity numbers are going to confirm that 100% identical, 99%, 99, 99, right? So we're finding sequences with this original blast that are very, very similar to the sequence that I put in. And so the question is, what if I don't want to find these very, very similar sequences? What if I want to find more distantly related sequences? And so the tool that we'll use for that search is called PSI BLAST. But first, I want to show you what's going to go into that PSI BLAST search. So if I click on this button that says multiple alignment, that's going to take me to a multiple sequence alignment of my original query sequence, which is shown across the top row, and then all of the sequences that were found below it as hits from my BLAST search. And so you can see that these sequences are very, very similar. So anywhere I see a dot, that is indicating that that particular sequence matches the original query sequence at that position. But you can also see that there are some positions that are not 100% identical. So for example, if I mouse over this letter that is showing up in my alignment, it's telling me that at this position, this particular sequence has a glycine, which is different from the original amino acid in my query sequence. And so as I look around this alignment, I can start to see that there are some positions that are 100% conserved and other positions that are less conserved. So for example, over here, where I see a number of glutamines and threonines aligned with the proline in the original sequence. And again, if I mouse over that, it will tell me that in the original sequence, this was a proline, but that only matches 27 of the 100 rows in the alignment. So this is an example of a position that is less conserved. And so the idea behind our PSI BLAST search is we want to make this more flexible. And so for positions that are 100% conserved, those are the important positions of the alignment. And we want to find blast hits that have the same sequence as those conserved positions. But for sequence positions like this one that are more flexible, well, maybe I am less concerned about getting an exact match there. And so again, this is the idea of that position-specific scoring matrix. Set up your scoring system so that conserved positions are not allowed to have as many mismatches, but more flexible positions are not penalized for mismatches at that position, because those parts of sequences are more likely to change over time. So when I run a position-specific iterated blast, or PSI BLAST. It starts from my same BLAST P search tool, but I'm going to scroll down to the bottom where it says Program Selection and just choose PSI BLAST before I hit the BLAST button. And so the first round of my PSI BLAST search is going to look very, very, very similar to my original protein blast. And so if I compare the hits here, I'm getting hits to the same things that I saw for my previous protein blast search, and I'm seeing the same very high percent identities, query coverage, etc. So I've found very, very similar sequences. So then notice that there is this column here of checkboxes that says select for PSI BLAST. And so what is going to happen is when I hit the button here that says Run PSI BLAST Iteration 2, the program is going to build a multiple sequence alignment of all of these checked sequences. And then it's going to run a BLAST search again using position-specific scoring. So setting up our search so that we are really, really following the original sequence for positions that are highly conserved, but we're not going to penalize mismatches at positions that are not conserved. And so if I click this button and say Run PSI BLAST Iteration 2, then it's going to start that process of building the multiple sequence alignment, constructing the new scoring matrix, and then it will go ahead and run the search using that position-specific scoring. And so these PSI BLAST searches can run quite slowly. So as I said, I've already pre-run this so you can see the results I get. And so as we progress through multiple iterations of our PSI BLAST, so this is actually the results of a third iteration. So I've run 2 successive PSI BLASTs. But what we'll see is that as we run more iterations and bring in more distant sequences, because we're allowing for flexibility at those non-identical positions, we'll start to find hits in our alignment that we didn't see before. And so in fact, these will actually be highlighted in the descriptions in yellow. So here is a hit that we would never have found without doing PSI BLAST. And so you can see that the percent identity is much lower. So we're down to 74% identity, but this is going to still be related to my original sequence. And the reason that we can find this sequence now is because if we look at the alignment of it to the original sequence, now we're allowing sequences with more mismatches to pop up in our blast hits. And that's based on the position-specific scoring where we're saying, yeah, look for matches at positions that need to stay the same, but if we know that there are some positions that can be more flexible, then we'll go ahead and allow some mismatches there. And so by running successive iterations of this PSI BLAST search, I'm trying to scroll back to the top. We'll see if it lets me do this. Oh, I'm all the way at the bottom of my list. But by running successive iterations of our PSI BLAST search, by continuing to click this Run button, we're adding more and more information to the alignment about which positions are always conserved and which can be more flexible. And so by running multiple iterations of PSI BLAST, we can find new sequences that are more distantly related to our original query that we would never have seen with just a straight protein blast search. So I hope that helps you as you work through some of our problems using PSI BLAST and BLAST, and I hope that helps you understand how this tool works. Thanks.